Okay, hello MYP3. This is your lockdown lesson on Monday the 1st of March. So it's all about simultaneous equations. We'll talk about what that means in a minute. But I want you to think of solutions that make 2x plus 5y equals 64 balance. And as you can see, I already thought of some possibilities. So if x was 2, 2x would be 4. So 2x plus 5y would be 64. So 5y would have to be 60. So y would have to be 12 to make that balance. If x was 7, 2x would be 14. So 14 plus something makes 64. 5y would have to be 50 for that to balance. So y would have to be 10. And basically you can think of any x value and figure out the y value that y needs to be in order to make the whole thing balance. So lots of possible solutions. X is 12, 2, y is 12, x is 7, y is 10, x is 1, y is 12.4. You can basically think of x is anything, including 0, negative numbers, decimals, and work out another value of y that will make the whole thing balance. So because there's an x and a y, you've got an infinite number of possible solutions that would possibly, or that you could possibly have to make that balance. Infinite possible solutions. So just pause the screen and write all that information down, please, including all the different examples and any more that you care to think of. Okay, so moving on. So again, this was in class obviously and not in lockdown. I've asked the class to find some pairs of solutions to 3x plus 7y equals 91, and here are some that were thought of in that particular class. So if x was 20, 3x would be 60, so 7y would have to be 21 for the whole thing to balance. So no, it would have to be 31 for the whole thing to balance. So y would have to be 4 3/7. And again, you can think of any x value you like and work out a y value that will make the whole thing balance. Or if you want to do it the other way, you can think of any y value you like and work out an x that will make the whole thing balance. So there's infinite solutions to that when you've got one equation but two unknown things. So again, pause the screen, jot that information down, and then maybe any other solutions that you care to think of. So, as I said, we can think of as many xy pairs of solutions as we want for 2x plus 5y equals 64, because we can just pick any x and figure out what y needs to be to make it balance. And similarly, we can find an infinity of solutions to 3x plus 7y equals 91. Again, you can just pick any x or any y and figure out what the other one has to be to make it balance. However, there is only one pair, x and y, that works in both 2x plus 5y equals 64 and 3x plus 7y equals 91 at the same time. Another word for at the same time is simultaneously, which is why this whole topic is called simultaneous equations. So we figure this out by, oh, by the way, just going back to that, pause the screen, copy the information down, please, and don't move on until you've done that. Okay, so we do this, we solve this, we figure out the x and the y by manipulating the pair of equations and adding or subtracting whole equations to each other. So I started off with 2x plus 5y equals 64, and I've labelled that as equation 1. And then I had 3x plus 7y equals 91, and I've labelled that as equation 2, and I've kind of bracketed them together like that to show that it's a system of equations that we're trying to solve together. And what I've done is I've taken equation 1, so that little yellow circle refers to equation 1, and I'm multiplying it by 3. So everything in equation 1, 2x plus 5y equals 64, I'm multiplying by 3. So 2x times 3 gives you 6x, 5y times 3 gives you 15y, and 64 times 3 gives you 192. So this new equation that I've labelled equation 3, is just everything in equation 1 multiplied by 3. And in a similar way, I've taken everything in equation 2 and multiplied it by 2. So 3x multiplied by 2 is 6x, 7y multiplied by 2 is 14y, and 91 multiplied by 2 gives you 182. So why did I do that? Well, the reason I did that was so that I could make the amount of x in both of these the same. So now they've both got a 6x in. So I said to myself, I'd like to make these x's the same. 2 and 3 both go into 6. So I'm going to multiply everything in both equations by something so that they've both got 6x in them. So I've just written in a little blue bubble there, or blue cloud. We did this to make the x the same. So we multiplied whole equations by something to make the x's the same. So the reason I did this was so that I could eliminate the x, because you can take whole equations from one another and eliminate the variables. So what I've got now is equation 3 and 4, and if I do everything in equation 3 minus everything in equation 4, then 6x minus 6x disappears, gone. 15y minus 14y gives you a single y, and 192 minus 182 gives you 10. So by eliminating the x's, we've managed to figure out what y is. Y equals 10. Now that we know that y is 10 is the value that's going to work in both equations, we can go back to our original equations and figure out what value of x is going to work in both equations. So moving on. Oh, and by the way, do write all of that down. Keep everything nicely lined up so that it's easy to follow. That's especially important in this topic. And moving on, don't move on before you've written everything. Now that we know that y equals 10, we can figure out x by substituting y equals 10 into the first equation, equation 1. So the first equation was 2x plus 5y equals 64. Now we know that y is 10, so that 5y bit becomes 50, and we've got 2x plus 50 equals 64, which we can manipulate to figure out what x is. Take away 50 from each side to get 2x equals 14, divide both sides by 2 to get x equals 7. So x equals 7 is the answer to this, and the whole solution, x equals 7 and y equals 10, is the simultaneous solution. That's going to be the two values, x and y, that are going to work in both of our original equations at the same time. At the same time being another word for simultaneously. So once again, pause the screen, write down the notes super neatly, and color coding, use lots of color to make everything nice and clear, line it up, and don't move on until you've done that. Okay, so having done that, x equals 7 and y equals 10 are the solutions. We can just check that by pumping them into the other equation, equation 2. So equation 2 was 3x plus 7y equals 91. That's equation 2. So if you stick x equals 7 and y equals 10 into that, you get 3 times 7 plus 7 times 10 equals 91. 21 plus 70 equals 91. And that is correct, so we know our whole thing worked by checking it in the other equation. So yet again, jot that down very neatly, please, before you move on. And moving on, so here's another example, but with the whole layout in one page. So I'd like to solve the simultaneous equations 3x plus 4y equals 104 and 32x plus 28y equals 248. So I've labelled them as equation 1 and equation 2. I've bracketed them together to show that they're a simultaneous system of equations. And then I've looked at the x's and I've said I'd like to make these x's the same. So I've got 16x and a 32x. Well, 16 and 32 both go into 32. So if I multiply everything in equation 1 by 2, then I'll have a 32x. And then if I just leave equation 2 unchanged, it'll have a 32x in it. So everything in equation 1 multiplied by 2, 16x plus 4y equals 104 becomes 32x plus 8y equals 208. And then the other equation, just leaving it unchanged, 32x plus 28y equals 248, and I've just written it there again, 32x plus 28y equals 248. So I've labelled those now as equation 3 and equation 4, even though equation 4 is just the same as equation 2. But they've both got 32x in them now, which is an advantage because then we can subtract whole equations from one another and do equation 4 minus equation 3 to give 32x minus 32x is going to disappear. So I've done it bottom minus top this time, equation 4 minus equation 3, just because the numbers on the bottom happen to be bigger. So 28y minus 8y gives me 20y, and 248 minus 208 gives me 40. So 20y is 40, and I've eliminated the x's. And dividing everything by 20, you get y equal to 2. So we figured out what y is. Then we need to substitute it into equation 1, sub in 1 I've written, to try and figure out what x is. So equation 1 was 16x plus 4y equals 104. That's just over there. But having figured out that y is 2, that becomes 16x plus 8 equals 104. 4 times 2 is 8. And now that I've just got a single equation with x in, I can manipulate that to figure out what x is. So taking away 8 from both sides, 16x is 96. Dividing everything by 16, a single x is 6. So I figured out that the other solution is that x equals 6. So the simultaneous solution is that x equals 6 and y equals 2. And I can just check that in the other equation, equation 2. 32x plus 28y equals 248 becomes, well, 32 times 6 is 192, plus 28 times 2 is 56, so it becomes 192 plus 56 equals 248, which is correct, so we know that it works. So this is my preferred layout for solving simultaneous equations. Writing down the two equations to start with, multiplying one or both of the equations up by something as necessary in order to make something the same, x or y, and then subtracting one equation from the other in order to eliminate x or y, Having done that, figuring out one of the variables, and then having figured out one of the variables, substitute it back into the first equation to figure out the other variable, and then having got both solutions, check it in the second equation, and if you've done everything right, it works. So this structure for a layout for solving these should be good for any problems that you encounter about simultaneous equations in MYP3. So here's another one, for example. Oh, by the way, just going back to that one, pause the screen, copy everything down super neatly, lined up, color to help you highlight things, and so on. Don't move on until you've copied everything super neatly. So moving on, yet another example, but you can see that the whole thing's got the same structure to it. So I've got my two equations. One's got a 3x and one's got a 6x. So I've decided to try and multiply them up so that they've both got a 6x in. So I've done everything in equation 1 and multiplied it by 2, and I've left equation 2 unchanged, so that I've got two equations now and they both have a 6x in them. So I've called those equation 3 and equation 4. I'm going to do everything in equation 3 minus everything in equation 4, just because the numbers in equation 3 happen to be bigger than the ones in equation 4. So 6x minus 6x disappears. 22y minus 4y gives you 18y, and 268 minus 61 gives you 207. So 18y is 207. Divide everything by 18 to find out that y is 11.5. And having found that 11.5 is equal to y, stick that back in equation 1. So there's equation 1 again. I've stuck in the fact that y is 11.5 to get 3x plus 126.5 is 134. I've taken the 126.5 from both sides to get 3x equals 7.5 and divided by 3 to find out that a single x is 2.5. So x is 2.5, and then I can check that back in equation 2. 6x plus 4y equals 61 becomes, so 6 times 2.5 is 15. 4 times 11.5 is 46, so it becomes 15 plus 46 equals 61. So again, it works. But you can see how it's exactly the same structure of solution that I used to solve the previous equation. I multiplied up to make something the same, x in this case. I subtracted equations from one another to eliminate the x. I substituted, and then I figured out what y was. I substituted my newly found value of y back into the original equation 1 to figure out what x is, and then I checked it all in equation 2. If you look at this solution and the previous solution, you're doing exactly the same thing, really. But of course, the answers, so they can be decimal values, they can be negatives, they can be 0, but the same structure to all the solutions. So once again, jot that down super neatly before you move on. Okay, so here's just an example from the book. So I've started with 2x plus y equals 3 and 3x minus y equals 7. And I'm saying that another way to do this is to notice that I've got a plus y and a minus y in the two equations. So I could eliminate the y by adding the equations to one another, because I've got plus and minus the same thing. So I could do 2x plus 3x gives me 5x, and then the y plus the minus y makes the y's disappear, and the 3 plus the 7 makes 10. So another way to do it, if you've got minuses in there, could be to add whole equations to one another to make things disappear. But otherwise, the structure to this is pretty well the same as the other solutions. So this is another one you can copy down as an example in your books. Again, super neatly. Don't move on until you've copied that.